volume dt, where volume just means the d-dimensional volume enclosed by the sphere that you draw. Okay, so that one made sense. The first term is just the expansion. It just tells you how much the sheet is being stretched overall. Tell it to change it. The next one is rotation. That's the omega piece. Omega AB is the antisymmetric part of BAB. This is sometimes called twist. So in Wald, I think this is called twist in a lot of the literature. It's pretty clear what the transformation does. The antisymmetric piece of this matrix just rotates the two components of zeta. So if we draw our circle at time 0, and then our circle at time delta t, the circle looks the same, but the points on the circle have been rotated on. So delta zeta is doing this. The last piece is this sigma component. So it's called the shear. We can write it or calculate it in general by taking the symmetric part of B and subtracting the trace, 1 over d BAA delta AB. There are two types of shear. There's the alpha type, which is sigma equals alpha minus alpha. This just stretches the x component and squashes the y component. So our circle gets stretched in the x direction and squashed in the y direction and turns into an oval. If we have just the beta off diagonals, this is basically the same matrix but rotated by 45 degrees. So that is going to do something like this to our circle, and that's called the shear. So something to note here is that shear transformations are area preserving. So the change in, we're squashing and stretching this circle, but we're doing it in such a way that the area enclosed inside the circle is held constant. And that's the fact that we chose it to be traceless. So we've separated off the area changing piece, that's the expansion, and we have these squashing and stretching. Now, we've talked here so far about one particular point on the sheet and what's happening to the nearby points, but it's clear that the full kinematics of this medium is going to be described by a vector field zeta A of x comma t, where in any point x we have the dynamics around that point zeta. Okay, questions about that?
For higher dimensions, are there different even more types of sheet, or is it all
there are more. So it should be the number of, it should be the rank of the symmetric traceless representation, which is getting bigger. Yeah.
So they're not orthogonal in a sense, or combined with rotations
To each other, you mean? I mean, these shapes are not orthogonal to each other, but these are independent pieces of the matrix B. So in that sense, they're orthogonal. It's kind of like for gravitation. It's like in gravitational waves. We have these are kind of like the two polarizations of the graviton, and they have the same sort of stretching and squashing effect on test masses. Okay. So after that brief foray into rubber sheets, let's go back to GR. So a few definitions first. So let O be some open region in the nano on a space-time manifold. The congruence in O is a family of curves such that exactly one curve passes through each point in this region. Passes through each point P in region O. So, for example, if this is region O, then we can draw a bunch of, oh, I just made them intersect, sorry. We draw a bunch of curves. So, okay, I need an infinite number of them, but you get the point. It's kind of like a coordinate, but it's different. Okay, so at any given point in the region, the point P, there's exactly one curve going through that point. And that means in particular that these curves will never intersect within region O. Now they might intersect outside region O. You know, if I messed it up again. Anyway, they can intersect outside region O. There. It's still a congruence in O, but it fails to be a congruence in this larger region. So a time like geodesic congruence is just a congruence where each curve is a time like geodesic. I'm not going to even bother writing that, I guess. Well, I'll write something. If each of these curves in region O is a time like geodesic, it means that the tangents to those curves give you a vector field mu alpha with mu squared equals -1 and obeying the geodesic equation in affine form. in the rubber sheet analogy, basically you're going to think of each of these time-like world lines as one of the points of the rubber sheet. One atom of your rubber sheet corresponds to one of these curves in the congruence. So now we're going to define, as we did for the rubber sheet, define a deviation vector zeta mu. So the way it's defined, let me draw a picture first. So it's defined so that if we start here at proper time tau naught, then it takes you to the nearby curve of your congruence, also at proper time tau naught. And then if you go along your time like geodesic by some amount of proper time up to tau 1, and so this is zeta, right? That's the vector zeta. And then we go up to a later time. These aren't necessarily parallel. So then we go to later time tau 1 and follow our vector field zeta. Then that'll take us to proper time tau 1 on the nearby curve. Oops. So that's how we want to define it. In formulas, what that means is that, first of all, it's orthogonal. We're going to choose it to be orthogonal to our congruence. So we have this vector field u. You can basically interchangeably talk about the congruence and the vector field of tangents. We have this vector field u that describes our congruence, and we're going to choose an orthogonal deviation vector zeta. Now that's not quite enough, because we also have to ensure that proper time along here, when transported, when you go by zeta over there, you go the same amount of proper time on that nearby geodesic. So how are we going to ensure that? That is the statement that zeta alpha del alpha u beta equals u alpha del alpha zeta beta. So let me tell you why that's why we want to impose that condition. Yeah, this is a Lie bracket. So this is a statement that zeta and u commute under Lie brackets. In other words, if you so u is the derivative operator dd tau along these world lines, and if you define a parameter s so that zeta is the derivative operator dds, then the statement that these two derivative operators commute is the statement that if you go delta s in this direction and then delta tau in that direction, that's the same as going delta tau and then delta s. So, do you want to say anything else? So, if I want to put this in words, say this ensures that tau 1 on curve 1 maps by adding zeta to tau 1 on curve 2.
this just the first order or anything, or?
Yes, this is all infinitesimal. Yeah.
Is S going to be space-time? Oh, sorry, is it going to be just space?
What?
I mean, you defined U by that geodesic equation, so you need to give me a parameterization of the family of curves.
You talking about U or? Sorry, say that again?
So you have defined U alpha with the geodesic equation.
That's right.
So that's an entire family of curves which you need to parameterize somehow.
Those curves are parameterized by tau. Oh, do you mean how we parameterize them within the family?
Yeah, exactly.
Um,
I guess that's the S parameter.
That's right, you can think of it that way, although we won't really need to use S. We could just think of the curves at any given point. There's a vector U alpha of x, which tells you about the curve that goes through that point. And that's going to be good enough. I don't think we really need to use DDS again. No, there's no torsion here. Torsion is like a defect in the geometry, so there's no torsion. There is going to be shear and twist, which I'm getting to in a second.
Should we be proportional to the Riemann tensor in any way or not? Take these expressions.
They will have relationships to the Riemann tensor because they satisfy the geodesic equation. Yeah. So first of all, before we get to the shear and everything, let me note that we can decompose the metric into a piece that's in the direction of the congruence and everything that's transverse to that. So to do that, we just write G alpha beta equals H alpha beta minus U alpha U beta. So this is the transverse or spatial piece of the metric. It satisfies U alpha H alpha beta equals 0. In other words, it's orthogonal to the congruence. You can think of it as the metric on these slices that are orthogonal to the congruence, although you can't always draw slices that are orthogonal to the congruence, so we'll come back to this. But roughly, you can think of it as that metric. It's a 4x4 tensor, but it has lower rank. It has rank 3. Okay, so by subtracting off this piece, you make it effectively a 3x3 tensor. So that's what I mean by that. So for example, if we're just in flat space, the original metric is -1, 1, 1, 1. And we choose the congruence to just be pointing in the time direction. Then H alpha beta would be 0, 1, 1, 1. That is, it just deletes off the time piece of your metric tensor. It's effectively three-dimensional, but it's still a four-dimensional tensor. So just as we did for the rubber sheet, we want to describe this congruence. We want to describe the time evolution of these curves thinking of them as these atoms in the rubber sheet. So define B alpha beta is rad beta u alpha. That equation that we had, hopefully still on the board, right here, this equation for the deviation vector. Implies that u dot grad theta alpha is equal to b alpha beta zeta beta. I'm putting a box around it because this is the evolution equation comparable to what we wrote down for the rubber sheet. So remember, for the rubber sheet, we said d zeta dt was some tensor times zeta. And that tensor described how it bended. So now this is the covariant GR version of that. It tells you what happens to zeta as you go along the congruence. So you imagine sitting on a particular world line of this congruence and using that deviation vector to see what's happening to the nearby congruences, just as we did on the rubber sheet.
Why is this only linear? I mean, the last one was,
The last one was also linear.
well, it also had,
These are all for infinitesimal, right? Because we basically have like a space-filling set of world lines, and this is the infinitesimal deviation of those. Other questions?
So do you get the like full, you want it more than infinitesimal, you would like expensive years?
I don't think exponentiating b would do it, because then you'd have to deal with all sorts of tricky curvature contributions. Yeah, I don't know. We're never going to do that. It's kind of like with geodesic deviation. When you talk about geodesic deviation, you really are talking about infinitesimally nearby geodesics. Now, you could calculate the deviation of two geodesics that are far apart, but that's just terribly complicated. That means you just have to go solve the geodesic equation for both of them, and then understand the geometry between them and find the deviation vector. There isn't really a simple way to get from the geodesic deviation to the finite variable. So it's kind of like that. It's a little confusing. We're going to have expansion and shear and rotation. I always find it a little confusing that a time-like congruence can have expansion. I mean, you have all these lines that are filling space. If they get wider, how can this? Okay, but it's okay. It's just like the rubber sheet. So you have a rubber sheet. It's filling space. You can stretch it. It's still filling space. It's not like even though you pulled them apart a little bit, there's still space filling, just like the rubber sheet. All right, if you still have homeworks, give them to Nima.